some students struggled some with parts of the assignment, so I just wanted to make a video to talk through how to solve some of these problems and follow up and try to help us, take another step in learning. So how many meters are there in 14 nanometers? Okay, so the question is going to be how many meters in equals 14 nanometers. And so the first thing is that these conversions are conversions in these prefixes, and the prefixes are going to be the same comparable prefixes independent of the base unit. And so we could have meters, we could have grams, we could have liters, we could have molar, which is big M, like that. And this is the first type of a conversion, and that is just conversion in these units. And we're either have to have memorized the relationship or be able to look it up in a table like that. So because we're going to need to know that relationship. And in this case, the relationship is that 1 meter, or one of any of these, equals a billion, 10 to the 9th nanometers. So 10 to the 9th, 1 times 10 to the 9 zeros, and a billionth, sorry. A billion. So a nanometer is a really small number. There, in 1 meter, there are 10 to the 9th nanometers, or nanomolar, or nanoliters, and so forth like that, okay? So that's the one thing that we have to be given or be able to get. The next thing is that in solving these kind of questions, there's really always there are always going to be 4 numbers in the question like this, and one of them is the unknown. And so we have to find out what the other 3 numbers are, and so that's the challenge. The next thing to say is that you were taught this, maybe not since way back in high school, but just to say, most recently you may have been taught it if you took or taken chemistry, and you can have an equation that looks like this, something like this. So there'll be this equal sign and a relationship between these 4 numbers, right? And these are our 4 numbers. And it turns out that that's the kind of classic starting point for this. But the first step is really to find out which one of those is the unknown, and then rearrange this equation so that it's equal to that unknown. And over here, we're going to have these 3 numbers. And it's going to look like that after we solve this. It's always going to look like that. And what's going on here is there's going to be a number that we are converting this to. Okay, so like in this case, the first number is going to be 14 nanometers, like that. And so what we're going to have is we always have to figure out where to put the numbers, like that, 14 nanometers, like this, and we have to put in both the number and the unit, like that. But the first thing to think about is the nanometers, and one way to think about it is that as this value increases, your answer is going to increase, and as this value decreases, your answer is going to decrease. And so that's called directly proportional to each other. And in one sense, this is a ratio of the number, 14, over just the number 1. It also is a fraction or a ratio. And these are as well. And we're going to figure out what to put in here, because what we're going to do is we're going to convert the units. And that's what this fraction is for. And we can make any fraction 1 over 1. And so we're just multiplying this times 1. But in doing that, we're going to convert the units. And the way to do that is to put the unit that you want to get rid of down here on the bottom, because this times this will have nanometers over nanometers, and they'll cancel. And then it's going to have this value in the denominator, or in the numerator. And that's going to be our meters, right? So then the next thing is we have to make a ratio of 1, where this is going to be 1 meter, and this is going to be an equivalent number of nanometers, and that's where this value comes in. The way I do these is I always pick the bigger unit, and I say, what if I had 1 of those? How many of the smaller unit would I have? and I'd have 10 to the ninth. And that's why I do it this way, because it's much easier to think of a big number than a really little number. And it's always good to think of the same thing and not switch it around. So you have the option to put the first number in and just put in a 1 meter. How many nanometers is that? 10 to the ninth from a table or from the web, like that, okay? And so then we just have to multiply these three, right, like that, by put these through, and we're going to get a really small number, like that. And so we're going to get a number that's like 1.4 times 10 to the ninth, minus ninth, like that. So how many meters are there in 1.4 nanometers? They're 10 to the minus ninth. And here's another way to look at that. And that is, I'll just put it in here. When we say that 1 meter is 14 nanometers, then this we could say is a 1 meter, and these would be 9 zeros. And as we go down, this is the first group of 3, and that's the prefix milli. And then this is the next prefix, that's micro. And this is the next prefix, that's nano. Okay? And they just keep going down. Okay? So if we had 1 millimeter, there would be a 1 here. If we had 1 micrometer, there would be a 1 here. If we had 1 nanometer, there'd be a 1 here. But we don't have 1, we have 14. So we have to go through this calculation, but there's also another check, and that is that these conversion questions, they're not going to change this number. They're just going to move the decimal point around. And so in this case, there is just a small amount of a meter in 14 nanometers. And so we would just slide the units over from here, 14 nanometers, and just slide them over 9 decimal units, placeholder units, and we get 0.00000014, like that, or 10 to the minus 1.4 times 10 to the minus ninth. And or maybe it'd be 1.4 times 10 to the minus eighth, sorry, times 10 to the minus eighth, because we're going to move it over to there just to express it. People typically would not express it as 14 times 10 to the minus ninth. They'd express it as 1.4 times 10 to the minus eighth. Okay, so let's look at another one of these. How many grams in 35 milligrams? So how many grams in 35 milligrams? So in this case, we're going to start with another small amount. So we're going to get a small number, less than 1, for our final answer. So it's good to be thinking about these, right? Because 35 milligrams is going to be less than 1. There are 1,000 milligrams in 1 gram, and that's just given from the table or from a lookup comparison on the web. So we can just set up our equation here, and we're going to have a number here, and numbers here and here, and a question mark number here. And we want to know how many grams. And we're going to start with 35 milligrams, and we're going to multiply it through this ratio. And we want to get rid of milligrams, so we put them in the denominator, and we want to get grams, we put those in the numerator. Now we just have to establish a relationship between these two. Well, there's 1 gram, I get to pick the big unit, and in 1 gram there are 1,000, or 10 to the third milligrams. And so when we multiply this through, we're going to get a final value of 0.035, and we're going to have milligrams over milligrams cancel, and so that's going to be grams. And so 0.035 grams. And so remember, we started out with 35 milligrams, and if we just started adding zeros, so that's 35 milligrams, we'd say that's like less than 1. So this is what the placeholder values are, like that, where this would be grams, and we're going down from grams, and we're saying there's 1,000 of these in a gram, so there would be 0.035 milligrams. And again, this is just a check. It was good to crank it, how to crank it through the math. And we didn't have to convert things or anything like that. And I think a scientist working in a lab uses it a lot, and I think that they often just look at it like this. And this is called the dilution ratio sometimes, or the conversion ratio. the scale ratio. The same type of approach is used when you're working with a map and you say, oh, 1 mile is equal to, 3 inches, like that, and you want to convert it. Or when you're working and you're saying, well, we're going to Boston and it is, 100 miles and we're going 60 miles per hour. So how long is it going to take us to get there, like that? And so these aren't all unit conversions, but they all fit into the same general strategy of having one unknown, and there are actually three known numbers or knowable numbers that we have to plug in. So there's another one, and I'll do some more of these just because I think it's helpful. So this is just to show the same story with molarity. It's all about the unit. So solution of sodium chloride, 10 millimolar. It would be the same for any, if we said, oh, it's not sodium chloride, it's lithium chloride, or it's glucose, it's the same calculation, and it's just that conversion. So we go from 10 millimolar to how many molar, and so that's another one of these where we're going to a smaller amount. So, how many molar in 10 millimolar? We just plug those in. It's going to have how many molar over here. It's going to have this ratio. It's going to have 10 millimolar here. We want to get rid of millimolar, so we're going to go millimolar down here and molar up here. And the big unit is a molar. The little one we learned is 10 to the third, 1,000 millimolar in 1 molar. And we multiply those through, and we get 0.01 molar. We don't have to write this 0, but if I write it in, you can see there are the three placeholders for 10 millimolar. 10 millimolar looks like that. This is the unit 1 molar, 1 gram, 1 liter, 1 meter. And then this is less. So this fills in, right? Think about counting like this. Here we started with 1 millimolar. That would be 0.001. Then we get 10 millimolar. That's 0.01. Then we get 100 millimolar. That's just 0.1. And then we get 1,000 millimolar. And that would be 1 molar. So that's all that's happened with these conversion questions like that. Yep. Okay, and then let's do a couple more because some of these actually have some challenges to them. So here's a solution that has a concentration of 0.01 mole per liter. What is the concentration in micromoles per liter? Okay, and so 0.01 mole per liter, and we want it in micromoles per liter. Okay, so let's just go over here. 0.01 moles per liter, and we want it to be how many micromoles per liter. So that one thing that comes in here is the second thing we have to say with regard to molarity. And I'll just add there are only three things we have to consider when we're talking about molarity. The first one is this a simple conversion question? We don't have to understand molarity at all to make a simple conversion question because it's just like we're converting grams to milligrams. This brings up a second one. The second one is that we just need to memorize that the solution of the concentration is given in molarity, and 1 molar is how that's said. 1 big N, 1 molar is equal to 1 mole per liter, and that's just always the case, and you just have to memorize it. So sometimes we need to be able to switch between the units, a molar and 1 mole per liter. So let's do that here, where we just pretend momentarily that this wasn't given to us. Instead, it was given to us as 0.01 molar, and we can ask, how many micromoles per liter is that? And it seems like, it's a big mismatch. How are we going to get those numbers? And the answer is we need to remember that 1 molar equals 1 mole per liter, and we don't do any math. We just rewrite that. So 0.01 molar is what we were already showing in the question. 0.01 molar is 0.01 moles per liter. And now we're ready to make this conversion, and you can see the liters aren't changing. So let's just switch this question up to make it a little bit more instructive. So this won't be the answer to the question that's in the thing, because we're going to say how many micromoles per milliliter. Okay? And so the safest way to do that is to say, well, I'm going to do two conversions. I'm first going to switch from moles to micromoles. I'm going to get that answer. Will I leave it at liters? And then as a second round, I'm going to switch from liters to milliliters. So let's just do that. So the first one is we start out with 0.01 moles per liter. We're going to multiply it by something, fraction, ratio, and then we're trying to get to how many micromoles, and we're just going to put in here for now in a liter, okay? And so we're going to go from moles to micromoles, and we just need to know that a micromole has, in 1 mole, there are 10 to the 6th, or 1 million micromoles. And so we can set that up here. We want to get rid of moles. It's in the numerator, so we'll put it in the denominator, and we'll put micromoles here on top. And we're going to say the big unit is 1, and the smaller unit is going to have to be a lot. It's going to be 10 to the 6th. So when we multiply this through, and I'm not checking this math, but I'm going to say we're going to multiply 0.01 times 10 to the 6th, and we're going to get 10 to the 4th, because 0.01 is like writing 10 to the minus 2. And we can multiply those through as using this scientific notation numbering system, and or just multiply through the values as given. And so then we're going to multiply mole over mole. That's going to cancel. We'll be left with micromoles per liter. So micromoles per liter. Now we're going to take that, we're going to multiply it through a fraction again to get, in this case, all right, final answer is we want to always get it to micromoles per milliliter. And again, I've changed that from the original question just to demonstrate this. And so here we're going to change not micromoles, but this time we're going to change the liter to milliliter. And see how it's currently, the liter is in the denominator, and we want to get rid of it. So we need to put liter up here and milliliter down here. And that's just because we want these to cancel, liter over liter. So we see we have to get rid of the one that's in the denominator, and we have to put it up here in the numerator to do that. Then we pick the big unit, 1, and the small unit is always going to be a big number, 1,000, or 10 to the 3rd. And so when we take 10 to the 4th times 10 to the 3rd, and then we get rid of those units, we're going to end up with 10 to the 7th micromoles per milliliter. And I could have made a mistake in that mental math, but that's the mechanism, and I'm just not double checking it by plugging it in, but I think that's probably pretty good. And so that's an example of that one. Great. And let's keep looking at these a little bit more. So then that's that one, and then we can go to this next page. So these, I think I'll just write on this page because these are just going to be moving those decimals like that. So in this case, we're going to want to say, well, we could write it. Here's that number. There's that number. And we could write it again as 43187.7 times 10 to the 1, because we moved it over 1 unit. And we can move it over 2, that'd be 2, 3, 4, 5. So this should be 4.31877. The number is not going to change, just the positional value times 10 to the 5th. And we could get that doing that like by this also. So see, this is we went down before and we got milli and micro and nano. And this is going this way. Now we're getting bigger. You'll be more comfortable with this because, right, these units are the tens, hundreds, and then we get to 1,000. Then these will get us to 1,000,000. like that. So it's the same idea. We have these groups of three numbers that are each corresponding to thousands and millions and billions and trillions. Same thing, only going the opposite direction from the decimal point, right? And so we can move this over like that and see that relationship like there. So here we could move this over. And scientists most typically write these scientific notions by having just the first number placement, so the tens number placement or the ones number placement is the first number, and then there's a decimal point. So for example, this one, we just want to move it over here, and this would be 1.03 times 10 to the minus 1. So less than, not more than. And so we just move it over one decimal point when we multiply that through. 10 to the minus 1 can be written like that, 0.1. So this one, we're just going to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 6 point, we have to write down all those numbers because we can't lose those. We're not changing the number, we're just changing the position. Times 10, I can't remember what I counted out. Was that 11? Times 11. Then this is just a 5, and we'd leave 5. We wouldn't write it differently. We would generally, scientists like to do that. They like to put, if it's 5, they like to put a 5.0 just to provide more of a confirmation that there's not a typo there. Okay, great. Just a couple more. This would be 1.18 times 10 to the minus 1. So we're just going to move it over. And and that's just the typical. The typical is to just move it over one decimal point like that. Here, this is a small number, and we could move it over like that, and it would just be 3.411921355 times 10 to the 1, to the minus 1. 10 to the minus 1. Because we're going to not multiply this by 10, we're going to multiply this by 0.1. Then convert the following to this to numbers. So here it says this is going to be a number, so we just move these over 5. So 1, 2, 3, 4, 5. So that's 770,188.98. And then this is moving it the opposite way. So we're going to move it over that way, 5 positions. And so we could have it be start here, it's going to be 0. Scientists also like this, put a 0.0, and then we're going to move it over 5 places. So I think this is it, right? 7777198. 1, 2, 3, 4, 5. And then this one is going to be 0.0, and then we're going to move it over 6. So like that, and like that, and like 1, 3. And then the next one is 4 points 10 to the 9th, so that for 10 to the 10th, so that's just going to be 4 with 10 zeros, or 40 billion. See, so we go from this up to thousands, up to millions, up to billions. 333, and we have a total of 10 zeros. This one is just going to be 92.26. This one is going to be 0.0681. So see, again, scientists like to put zeros on either side of the decimal point, or at least represent those. So we'd have like a number like 5.0. Scientists like to write that just to show that you've followed it to that detail. Sometimes there are more significant digits depending on the experiment and the techniques. Okay, and so I'm going to stop there, and that's all there is to that. Thanks.